Hello guys, I'm back. Do you want to know how to identify control loops in the pipe instrumentation diagram? Moreover, do you want to know how chemical process engineers do P&ID tuning in real life? This video is for you. My name is Jeferson Costa. I'm a chemical process engineer with expertise in plant design, and this is the best channel to learn everything that you must know to work with plant design. So subscribe to this channel now and let's start this content. In this video, I will share with you at least answers for 80 questions. How to identify a control loop in the pipe instrumentation diagram? What is P&ID tuning? What are the P&ID parameters? What are the ways to do P&ID tuning? Which heuristics methods are available for P&ID tuning? How to do P&ID tuning on Aspen Hysys? How chemical process engineers do P&ID tuning in real life, and many people asked me about books. So which book can help you to learn process control and P&ID tuning? Just before I start, let me alert you that everything that I teach in my social media are based on practice. I like to share what happens in real life with you in order that you get skilled in chemical process engineering, plant design, and it is the way that I do with my students. So don't expect for many equations, integrals, or Laplace transform, because I will not share this kind of information with you. What I show to you right now is what I do in real life as a chemical process engineer. And to begin with, I will teach you how to identify a control loop in the piping and instrumentation diagram. In this piping instrumentation diagram, you see a flow controller, and the elements of this flow controller are the measurement device. In this case, we have orifice plates to do the measurement of the flow. We have some manual valves, and we have the flow transmitter that is responsible to send the information for the PLC, where we find the controller. And the signal from the controller is sent for a control valve that is responsible for opening and closing for reaching the desired set point. Here we can see that for reading a pipe instrumentation diagram, you must be familiar with the nomenclature. So here we have Fe that represents the flow element. It is the element responsible for doing the measurement of the variable. We have the Ft that represents the flow transmitter, and as I told you, sends the signal for the PLC. We have here the FIC, flow indicator controller. So this signal goes to the PLC not only for informing the value of the flow that is measured in the field, but also for controlling some device to have the desired variable at the set point. Here you can see also the H and L. They represent alarms associated for this controller. So if the flow is high, the operator will receive a signal or an alert in the control room talking about that, alert them about that. We have a low alarm, so if the flow is low according to the set point, the operator will also receive alert at the control room to know about that. And we have here a totalizer. So we have a flow quantification indicator, and this quantification is done inside the PLC, and this is a signal of data. The dashed line represents a signal of electrical signal that sends to a converter, a signal converter that goes to the actuator of the control valve. This is a FV, flow valve. In some cases, you can find this nomenclature as FCV or flow control valve. And we have here a solenoid to actuate faster the valve in a case of incident, accident, or something that is important to the fast shutdown of the valve. That's why we have the SD here as a signal going to I that represents a safety interlock. So here we see a control loop and how it looks like. Now let's take a look in another P&ID and in another kind of control. In terms of drawing, this P&ID uses the same standards as the previous one, and in this part of the process what happens is that we have a gas stream saturated with water, and to remove the water from the process I use a heat exchanger. Downstream of the heat exchanger I have two phases. I have gas and I have condensate liquid that must be separated in a vessel separator. At the top of the vessel separator, and you can see a representation of a demister, we get the gas, and we have at the bottom the removal or the withdrawal of the liquid. And to guarantee a minimum or the best level in this vessel, we have a controller here, a LIC, that represents level indicator controller, that sends a signal for a control valve that is the LC, level control. And why it's important in this case have this kind of control for this. This gas that is going out, or that is flowing with the condensate, it's a flammable gas, and I need to guarantee a minimum level in this vessel. So I cannot allow that I lose the seal of liquid, because if I have that, I will send gas to undesired place. And that's why I have in the level controller the LALL that represents a shutdown condition if my level gets very low, and I have the LAHH that is a shutdown condition because I don't want to send the liquids to a part of the process that shouldn't receive liquid. And in this specific case, I have a level transmitter and also a switch, a level switch that is, although I have the shutdown with the level transmitter, I have another device to guarantee that if I reach a high condition, I will also shut down the plant. So it improves the safety of the process in terms of preventing over level in the process. And as you have seen in the previous control loop, we need to have a source of measurement. So in this case, we have the level transmitter that is measuring the level in the vessel separator. This signal must be sent to the PLC where we have the controller. So we have the measurement, we have the controller, and we have the control valve. Something that is interesting to note is that close to the control valve we have a FC. This FC represents the safe position for this control valve in a case of failure of power. That can be electricity, can be instrument air, can be any situation that requires the valve to go to the safest position. And FC means fail close. So if I lose instrument air, what happens to this valve is that it goes to close position. And let's take a look in another P&ID now. Now you are seeing another P&ID with different standards for the drawing, and it is also another process. But the concept is the same, and in this case what we have here is a controller and pressure differential valves to control the differential pressure between what is going upstream of the heat exchanger and going out at downstream of the heat exchanger. So we have the PDC, that means pressure differential controller. It takes a tab at the discharge of the heat exchanger and at the inlet of the control valves. This measurement is sent to a PLC also, and the output of the PLC goes to two control valves. See that this control loop is different from the arrangement, is different from the previous one, because now we have a split range control. So part of the signal will actuate in the small valve, control valve, and the remaining signal to the process will actuate in the biggest control valve. Or it can be the opposite, depends on the control philosophy of the plant. So it's important that you get familiar with that. It can be in the operating manual or eventually in the interlock description of the plant. Different companies has different kinds or different ways to do the pipe instrumentation diagram. See here that in fact what we have in the field is a tap with manual valves to isolate the PDC, and this PDC must be a transmitter, because if it's not a transmitter, it's not possible to send the signal to the PLC. But the way that the company draw its P&ID don't represent this kind of information in the drawing. It's not wrong, it's not right. Each company has its own way to do things. And what is interesting, most often what we have for control valves is isolation valve at the inlet, another isolation valve at the inlet, at the outlet, and a bypass valve, in order that in a case of maintenance or in a case of replacement of any one of the control valves, the operations can close the segment, drain that, remove the fluid that will be trapped here, and operate the plant at the bypass. See that for isolation, in this case, we have ball valves, that is the representation for this company, and for the bypass we have globe valve. That's important because different types of manual valves are used for different purpose. And finally, to finish this part related to how to identify the control loops in your pipe instrumentation diagram, I share with you now a pipe instrumentation diagram representing a reciprocating compressor. I use this P&ID very often because it is very rich of information for freshers and also for students that wants to work with chemical process engineering and plant design. So to start with, to identify the control loops, you need to look for the controllers. And the controllers most often are squares inside cycles with the last letter SC, C of controllers. In this way we have pressure indicator controller, we have pressure indicator controller, and we can have some others controller here that I will not get attention right now. In this kind of controller, it's different from the both previous one, because now we have an override control loop. It means that depending on the signal of the PIC 254A, or depending of the signal of the PIC 251 or of the HIC 251, the PY will send the information for the control valve that in this case is responsible for the recirculation of the reciprocating compressor. Some things to observe. At the suction of the compressor, we have a pressure transmitter. As I told you, we need to have a measurement element. In this case, it's a pressure transmitter, and we need to send the signal for the PLC that is represented by this square and circle with information within. In this case, we have the alarm for high pressure, we have alarm for low pressure, and we have a symbol here for the permissive conditions. If one condition is not achieved, the compressor is not able to start. And one information, we have information also for the shutdown. So we have the pressure switch low and the alarm associated with that, and some companies will use the losango, and you can see that kind of recommendation in the ISA, where you identify which kind of interlock is associated with this control loop. And information that we have not seen in the previous pipe instrumentation diagram and is not shown too often is the action of the controller. If the controller is the direct control or reverse control. In this case, for the suction pressure controller, we have a reverse control. In the other hand, for the discharge of the compressor, we have a direct action. And let's understand what it means. When this recirculation valve will get the gas from the discharge of the compressor and will send to the inlet of the compressor. The main purpose of this PIC 251 is to keep the suction pressure at a desired condition. So if the pressure decreases and I need to return my pressure to the desired condition, what happens is that the signal that I will send to this control valve is for opening. I am reducing the pressure at the suction, and I will increase the signal to this control valve opens. So I have reverse conditions for my process, and because of that is reverse. Now let's take a look at the discharge. In the discharge, I want to let my discharge at a desired pressure also. So if the pressure at the discharge increases, I need to open my control valve to reduce the pressure. So you will always compare the situation, what is happening with the variable that is being measured with the desired condition that you want to. So to relieve the excess of gas that I have at the discharge, I need to increase the signal to my control valve. So as I increase the value of the variable and I need to increase the value of the signal to the control valve, I have a direct action. In the opposite, as I reducing the value of the process and I need to increase the signal to the control valve, I have reverse action. This is a rule of thumb. This kind of condition depends a lot if the valve is fail closed, if it is fail open. It is a good way to identify the action of your control in the piping and instrumentation diagram. Now that we already talked about how to identify the control loop in the piping instrumentation diagram, it's important to understand what is PID tuning. To help you to understand what PID tuning means, let's take a look in this graph. In this graph, what is happening is that every time that the control valve opens or closes, the main target is to reach a desired set point. But if the values that we need to do the settings of the controller are not good enough, we will not be able to reach that kind of smooth conditions or steady state conditions. So you can see here that we have some variables here and it is going up, going down, going up, going down, and in many cases, in most of the cases, to be more precisely, we don't want this kind of situation. Your control valve can open and close, but your variable should be as much stable as possible. So let's compare this picture with the other one that I have to show with you. Here we have some others variable, but what it's important to understand is that the black line is my set point, and my variable is around the set point. And when I change the set point, in this case here, there was a little increment in the set point, the variable went to the other level of variance. And the red line represents the opening of the control valve. Here the range is very small, so it's not so visible to see the changes in the control valve opening, but there is, because without changing, you can imagine that the variable will not reach another level. So the importance, what is the P&ID tuning, is select the best values or the correct values to set your PID controller. And to understand better what is the PID, we need to know what are the definitions of PID. The term PID is different from P&ID. P&ID means pipe instrumentation diagram, and PID means proportional, integral, derivative actions that you have in a controller. Most of the chemical and petrochemical industry uses a PID controller, although not necessarily you need to have a value for the derivative part. Most of the process runs well with the proportional integral control philosophy, and we'll see a little bit about that in some minutes using the Aspen Hysys. But to understand better the terms, let's take a look here in some definitions. Let's take a look in the definition. Often called P constant, the proportional term can be referred to as proportional gain, Kp, or others, which is not a unit but instead a ratio. Can also be called proportional band and measured in the units of percent. So you can see that the Kp is not, there is not a unit for that. And when using the Ziegler Nichols method, you will see that the definition for the integral and derivative depends on the calculation of the proportional term of your PID controller. And while during the settings of the PID, you will see that in fact we don't have a unit of measurement, only if we are talking about the proportional band that we can have that identified as percentage. It is the proportional band that determines how fast is the response of your system. I usually tell my students that the Kp, that is the proportional band, represents how big is the opening for a control valve each time that it opens. So if you are doing your control and your Kp is big, for when your valve opens, it will opens too much, and if you have flow, for instance, your flow will increase a lot. And if you reduce the Kp, the chances are, depending on the other parameters, that you will do is a small increment in the opening until you reach the desired set point. It's important to mention that if you have a controller that only uses the proportional band or the proportional term, you will never reach the set point. You will always have an offset between the set point and the value, the present value. To reach the set point, you must have the integral part of the PID controller. The integral term, as known as reset, is a function which adjusts the proportional bandwidth with respect to the set point to compensate the offset from the set point. And this parameter determines how fast the steady state error is removed. So the integral part of the PID will do calculations related to the error, and the error is the present value that you have in your variable compared to the set point that you desired, and it will be responsible for reducing this error to the steady state condition. And just to complete the integral term, it can be expressed as repeat per time, minutes or seconds, or time per repeat. so we can have seconds per repeat, and that changes everything when we are doing your PID tuning, because the value that you are adding is the opposite. So it's very important to you be familiar with that in order to be able to fill the correct values at the correct place. In talking about the derivative term, also known as rate, it senses the rate of rise or fall of system variable and automatically adjusts the proportional bands to minimize overshoot or undershoot. The purpose of the derivative constant is for predicting change. The derivative action x of the rate of change measured in the process variable. It is usually measured as time, so it is seconds or minutes, and the main purpose of the derivative term is to predict what can happen in your variable. So it's most useful when you have a dead lag, that is when you do a change and you have a long time to have a response in your system. When you have systems that are too fast, the D term of the PID is not used too much. But when we are talking about temperature control, usually we can use the derivative to have better response in our control loop. We talk about the PID definitions, but what really matters for us in the field is how we set the correct values in the field to have a stable control and have the plant is running smoothly. So to define the best values for KP, TI, and TD, that is the proportional, integral, and derivative terms, there are some ways to do that. One of the ways, and that is I most use, is the manual way. So I set values here and I identify what happens in the process, and I will talk with more details about that during this video. And another way to do that is, depending on the controller that you use, it has a function of auto-tuning. So the programming will be responsible for identify the changes and do the calculations and get the best tuning for your process. I didn't get in touch with this kind of control yet. I cannot say to you if it is expensive or not. And there is another way to do the tuning, that is using heuristics methods to preliminary define which are the best set points, which are the best values to add in your PID controller. One of them is probably the most famous, is the Ziegler Nichols method, but there are others, and I will share with you which are the equations and some general information about that. And after that, we'll go to the Aspen Hysys to verify which happens when we change numbers in a control loop. One of the most known heuristic methods for PID tuning was developed by Ziegler and Nichols. The authors developed two kinds of approach, and at the first time they used a closed loop to define the values for the PID parameters. After that, they developed another kind of approach, in this way using a closed open loop based on a first order process. In my screen you can see the equations for both of them. In the first approach developed by the authors, the objective was to increase the gain of the controller until the process gets unstable in a cycling way. So based on that, they could measure the ultimate gain and also the ultimate period. And based on this both information, the user would be able to define the values of KP, TI, and TD. The main disadvantage of this method is that for real application, to stress a system to oscillate at its limits, it's not something trivial, because as you know, we are talking about chemical petrochemical process, and deviations from the process can lead to accidents, incidents, and etc. So because of that, they developed a second approach to define the values for the KP, TI, and TD. The second approach was based on an open loop. In this way, instead of using the ultimate gain and the ultimate period, the nomenclature now used would be the delay or dead time, time constant, and also the steady state gain. And what happens in this case is that in an open loop, the user do a disturbance in the process and observe the response of the variable. And based on the dead time to observe some kind of modification in the variable, and also how much time it gets to produce 63% of the final result, and also with the calculation of the deviation of the variable and the disturbance, the user would be possible to define the KP, TI, and TD. But the Ziegler Nichols method is not the only one available in the market. You can see here in my screen that we have other authors that propose similar approach to solve the P&ID values needed to do the P&ID tuning. Some of them is CHR method that was developed by Chen, Horns, and Heswick, and we have also the Cohen and Kuhn, but many others are available. And the approach is very similar, using the time constant, the dead lag or dead time, and also the constant gain. The user are able to define the values that best fits for the P&ID controller. Something to mention is that each method best fits depending on the process characteristics. So here you can see two graphs, and to the same process conditions and to the same disturbance produced in the process, depending on the kind of process, we can have the Ziegler Nichols, and you can see a lot of deviation, and the CHR with a small deviation. And in this other process, we have a lot of deviations, and some methods are more stable to the deviation, to the disturbance in the process than the Ziegler and Nichols. In any case, these methods can be useful for the first approach to define the values to add in the P&ID controller. How easy to do that depends on the process, because here when we go to the field, we are not dealing with equations, we are not dealing with Laplace transfer or other kinds of differential equations and etc. We need to evaluate the process, we need to do changes in the controller, we need to evaluate the process, and based on that define which are the best values for the P&ID. Now I will start the Aspen Hysys, and we will see how is the behavior of a controller when we change the values of KP, TI, and TD. So guys, we finally reached at the funny part of this live session, that is dealing with the Aspen Hysys. The Aspen Hysys is a useful tool to do steady state simulation, but you can use it also for dynamic verifications. What is important to you understand is that, in my point of view, the most benefits of using the dynamic verification is when you have the real data of your process. So we need to define, or we need to add to the dynamics information related to CV of the valve, and if you don't have the real CV installed in the field, you will not get the most benefits of this tool that is available in the Aspen Hysys. And we need to add information for the equipment and etc. So here I already built the process simulation with the controllers, and I will not start from scratch with you. If you want to know how to start from the scratch dynamic process simulation, you can take a look in the video that I already recorded and is available in my YouTube channel. The link is in the description of this video, and also maybe one alert, you will see here one alert if you are watching this in the YouTube. My main purpose here with the Aspen Hysys is to show you how to set the graphs and some settings that are needed to do the Aspen Hysys run in the dynamic mode. So let's go to the dynamics. We need to tap dynamic modes, choose to switch, and here everything is already ready to run. So let's verify the controllers. As I told you, it's important to know which kind of controller we are using to set to the Aspen Hysys if the action is reverse or direct. In this case here, we have a process very similar to the one that I have shown to you. We have a gas stream with condensate and a vessel separator. So just for the matter of teaching, I added a flow indicator controller here, so I can control the flow that goes to the vessel separator. And we have also a level indicator controller to control the level of the system. In the Aspen Hysys, we need to define the set point. The PV is the present value calculated by the Aspen Hysys, and we have the output or the opening of the control valve. Some information that's important to add is the minimum range, maximum present value range, and in terms of P&ID tunings, what we need to inform is KC, TI, TD, and depending on the algorithm type, you have different nomenclatures and also different information. It's important to you understand that depends on the controller vendor, the information that we add to the P&ID can change. For instance, as we have seen, the integral part of the P&ID can be informed or expressed as time per period or period per time. So if that changes, the value that you need to use changes. And just to let you know, take a look, and I encourage you to shift from algorithm type. So when I change for Honeywell, the parameters changes. When I go to Foxbottle, the parameters changes also. And when I go to Yokogawa, the parameters change again. So the KP is the proportional part of the P&ID controller, TI is the integral, and the TD is the derivative part of the controller. So to start evaluating what's happening here, we will activate the faceplate, and the faceplate shows to us the set point, the present value, and the opening of our controller. And we will add also the strip chart, because the strip chart helps us to identify what's happening in terms of graph. So here, by standard, I will use the set point, the PV, and DOP. It's very important when you are evaluating P&ID tuning that you observe not only the PV reaching the set point, but also the opening of the valve, because when you are doing a P&ID manual tuning, observing the behavior of the opening of the control valve, you have the feeling to know if you need to increase the KP, or if you need to increase or decrease the TI, and etc. So I always use also the OP as a variable that I observe when I doing the P&ID tuning of a control loop. So we need just to click on create and display. What is interesting to you know, if you don't know yet, when you click with the right button of your mouse, you have the option to do the dockable of this window. So I will use that, and I hold this. I can let this at my right side or left side, wherever I want to, what the region that best fits for me. And I will do the same for the LIC controller. So in this case, we have a direct controller. Remember, if my variable increases and I need to increase the opening of the control valve, I have a direct controller. So to return to the set point. So this is a rule of thumb and depends on a lot of characteristics of the system. And here I have also this, in this case, as I'm talking about level, my level is from 0% to 100%, and I have here the PID parameters, and for a while only the KC is available, and I will change that for Yokogawa because this way I have the KP. With exception for Foxborough, here the others algorithm type use the same value. So if I change from KC to KP, it keeps the same value, but when I use the Foxborough, the calculations are different, so they use different values. So now what I will do is the same thing, add the faceplates to the process simulation and also a strip chart, create and view, and I will dock this also, and I can use the same part of the screen to share two graphs in my screen. So here I have at the upside the flow indicator controller, and at the bottom side the level indicator controller. Just before starting running your process simulation dynamics, is interesting to go to integrator, and we can decrease the velocity of the information that you see in this screen. Here, by standard, it is at 1. There is no acceleration and no deceleration. So what I want to see is slowly what happens, because when we are talking about pressure, when we are talking about flow, usually the changes are very fast, and when we are talking about volume, depending on the how much flow we are handling, it can be very fast. So just to verify what will happen, let's decrease a little bit the response in the graphs, and now we can click on run. Remember that for this time I just have the KP of the process. I didn't add the integral nor the derivative. And just before click on run, I will change for auto, and let's see what happens. So my process is already running, and here I have another way to verify the results, what is happening. If I click on turn, and if I go to monitor, I can verify that my system is very unstable. As you have seen in the first approach to the Ziegler and Nichols approach, it was the behavior that they would like to verify. Cycling, disturbance, and with that do the calculations for the ultimate gain, ultimate periods, and with that define the KP. In this case, I am already dealing with the KP parameter. So what I can do here, to have a more stable condition to my process. First thing is that you can see that one point to another, the process, the opening of the control valve is too fast. It goes from 0 to 100%. And sometimes, most of times, when we are dealing with the dynamics in the Aspen Hysys, you will have some kind of abnormality. As you can see, the graph disappeared. So what I will do here, first thing first, I will do the decrease of the Kp in order to decrease the response of the system. When I do that, you see that my graph already responded, and I am able also to change the range or the time range that I have here. So let's click with the left side, the right side of the mouse, click on control, and if I go to axis, I can use the auto scale, and I can define also the delta time that I want to evaluate. So here I will increase that to 30 minutes, and in the axis, as I'm talking about the percentage, and I can see all the information in my screen, I will let as it is. Just to have the same effects, let's change also here for 30 minutes. And in this way, we have both graphs at the same basis, time basis. So what I have here? I have here the blue line represents the opening of the control valve. I have the green line that represents the present value of the control valve, and I have the red line that represents the set point. When you are doing, when you are turning a PID controller that has only the proportional part of the controller, you will never reach the set point. You will always have an offset if your control loop is stable, or you will have values above and below the set point if your proportional gain is too high, so it is in unstable conditions. So now to get closer to the set point, I need to introduce the integral value for this process. So here at the first site, I will add S1, and let's verify what's happening and observe that we will have changes in this case only in the flow controller, because I'm dealing only with the flow controller at this time. And now the PV already reached the set point. In the Aspen Hysys, it is very easy because there is no effect of environment, there is no effect of the increase in pressure drop because of your pipe or pipelines and etc. So this is a reference to you deal with the controllers of the system, but it is don't represent the real life if you don't have real life data to compare the results. So stay alert with that. So in this case, I can conclude that my tuning to the PID of the controller is okay. So now, just to verify the behavior of the system, I can change the set point. So let's increase a little bit. And let's decrease a little bit. Just to let our life easier, let's use auto scale. Now let's change again. You can see that the red line and the green line matches one with another. So very fast response. To see that slowly, as I told you, what you can do is you can stop and go to the integrator and verify if it's possible to let the system more slower. So let's return and let's do the changes. Now you can see that the graph is slower this time. So you are able to verify what's happening in the control. Another way to verify is to use the monitor and see the behavior of the system, but the most not the most reliable, but the best way to verify the response is using the chart. So this is how the P&ID tuning is set in the Aspen Hysys. In the Ziegler and Nichols method, what they mention to you to do the tuning, the procedure that they recommend you to define the numbers for the P&ID tuning is to let your control loop in manual and add a disturbance. So for instance, here I have a 13 opening, and I will add a disturbance in the system, for instance 45%, and I will verify the graph and look for the dead lag or dead time. I will look for the time constant and also for the gain of the process, because now the set point is not matching with the present value. So this is the way that the Ziegler and Nichols recommend you to define the values for the P&ID. This kind of the method can be used in the field, but you must be alert about the limits of your system to not go to unsafe conditions. And it depends on the kind of variable that you are evaluating, because to define the time constant and to define the parameters based on this method, you need to have a stable method, a stable process. But not all the process keeps it stable when we are dealing with the process in manual. For instance, let me return it to auto, and now let's deal with the level. The level is in auto. I didn't set any parameter for integral, so we have only the proportional. So this way you can see that my vessel is empty. And in real life, if the vessel is empty, I need to make sure that my valve is closed, because as I told you, I have a flammable gas. I need to keep the liquid sealing in this vessel to prevent sending flammable gas to undesired conditions. So here I can start on auto, So here I can, as we know, here if I want to increase the level in the vessel separator, I need to close the valve. And here we have a direct response, because to keep the present value at the set point, if my variable increases, I need to open more the valve to keep the same level. So what I can do here to have some kind of level in the system is having on manual, and this opening is too big because I'm not filling the valve based on the amount of liquid that is going into my process. So instead of having 8, almost 9, I will consider 5% of opening. When I decrease the opening, I expect to have an increase in the volume, but I don't reach that. So let's increase more. Let's decrease more to 1% opening. Now I am starting having the increase in my process. So now I start to increase the volume of the level of the vessel separator. And here we can imagine that this vessel separator is too big to the amount of liquid that we have in this system. The calculation or the sizing of a vessel separator depends on two things. The first one is the amount of gas that is going in, because you need to have the velocity that goes to the vessel separator. So it defines the diameter of the vessel separator, and we need to define the hold up time that we want to have, if it is 1 minute of liquid, 5 minutes of liquid, depending on the standard that you are using or the procedure that you have in your company. So I didn't do the sizing of these. I didn't use these criteria to define the size of this vessel. I just add a handle value to do this class for you. So, but you can see now that the amount of liquid is increasing, and differently from the flow controller, if I add one value here of opening, my system will always be increasing, because the amount of flow that is going in is less than the amount of flow that is going out. And I need the PI controller to let the controller able to or close the valve or open the valve to have the best to the level reach the set point. Here you can see that is decreasing, so 1% is too much. So now what I will do, I will go to the settings. Let's define the KP and TI, and let's add it to auto and verify if my system responds. And the set point here was 0, so I want as 15%. So as my present value is below the set point, my valve closed, and now it's increasing the PV. The vessel is filling. Eventually, every time that you change the set point, your controller can have an unstable condition, because the calculations of the error, that is the value, the present value, that is the differences between the present value and the set point. So you have seen a bump there, but that's why interesting when we are doing the PID that most of the controllers asks that we let the controller to manual, do the changes in the KP, TI, and etc. And after that, we return to auto. So here, guys, we have the PID controller in the Aspen Hysys. But the class is not over. Now I want to show you how we do the tuning in the field, in the real life, how it happens in the real life. So what happens when we are doing the commissioning and startup of a plant? One of the activities that we must do is the PID tuning of your control loops. You will get the piping instrumentation diagram, will verify which are the control loops that are available there, and you go to the control room or in the HMI available in the field, and we'll look for the controllers that was programmed by the automation engineering. And here now you can see a sample of a screen that is available in the control room for a process where I have the production of where I have a distillation. So you can see some controllers here. You can see the LIC 310, the LIC 321, and the others information. It was hidden because it's not necessary for these teachings. What matters here for us is that I have a control valve, I have a controller, and associated to that I have a level transmitter, and I have a PLC, and etc. So how the chemical process engineer will do the tuning, or the commission engineer will do the tuning of the control loop? Most often we click 2 times in this kind of information, and a submenu will open to us. So in that example, when I click 2 times in the controller, I open a submenu, and I have the option to do the setting of the tuning, or I have the options to do the tuning of the controller. And here, depending on the vendor that your company uses as the source for the automation, for this case, I have information related to the set point, to the OT, that is the opening of the valve, and I have here the gain in percentage. As you can see, as we have mentioned, the proportional part is a ratio, but it can also be represented as a percentage. So the gain here is the same value of Kp that we have in the Aspen Hysys, for instance. We have the reset in time per repeat. So here is the part related to the integral of the PID, and I have the derivative that is in time. So in this case, I have the integral part is minutes per repeat, and I have the derivative as minute. You can see here in this control loop, the derivative is 0. Based on the tag of this control loop, it is pressure control, because I have a PIC, pressure indicator controller 504. Some other information that you can find here, and it is useful for your operations. Sometimes you are able to limit the maximum opening of your control valve, or you can limit the minimum opening of your control valve. For instance, you have a process that you need to have a minimum flow through the control valve for any reason, so you can set the controller to have not close below 5%, 2.5%, 10%, and etc. Or the same, you usually in startup, the controllers can get very confusing, and unstable, so you can set that the controller should not reach more than 70% of opening, and it's possible to do this kind of thing inside the controller. Here, in this specific case, you are able to inform the controller action if it's reverse or if it's direct. There are information for deadband. There are information for the high span, which are the value for the high span, for the low span, and track the PV. Sometimes you want that your set point follows the PV. So all of this is you can find in the field. I have other examples to share with you. In fact, I have two more examples. Here we have other kinds of PID controller, and in this case, the organization of the information are that at the top side, we have information for the present value and the set point, and at the bottom side, we have information for the opening of the valve. And when I click on settings, I will have another submenu that will open, where I will be able to inform the value of the gain, that is our KP, informing also the integral of the PID, that in this case is minutes per repeat, and I have also information to the derivative, that is in minutes. This is simpler than the last one. As you can see, I am not able to strafe inform if it's direct or reverse control, or if I can limit the upper opening or low opening of the control valve. But each project is different, each company is different, and you can find this kind of situation when you are dealing with chemical process engineering, plant design, and going to the commissioning and startup of a plant. And finally, I have another PID for a controller here. So in this case, is for temperature, because it is a temperature indicator controller 801. And here, when I click in the TIC, I open this menu where I can see the set point, I can see the present value, I can see the opening of the valve. In this case is OV. Sometimes you will see this as OP or as OT. It's the same, it's synonymous. And I have the values for introducing the KP, the TI, and also the TD. In this case, as it is a temperature controller, I used the TD to help me with the process. And just to give you a reference, I had a system with this behavior, and when I did some changes in the process, I got this other one. And you can see that it is much more smoothly and much more stable than the previous one. Just before I suggest you some books to learn more about control and PID tuning, I would like to mention that the subject control and PID tuning can be very, very tough, and can be very complicated depending on the focus that you are giving to your studies. If you are automation engineer and you need to deal with the equations to programming inside the controller, you need to know a lot about the equations, about the differential equations, Laplace transform, etc. But in the point of view of the chemical process engineer working with plant design and being in the field to run the plant, all of this is not necessary. What we need to understand is that we must define the three values of the PID controller. We need to make sure that any adjustment in the controller will not lead the process variable for unsafe conditions, and we need to verify if our set points for alarms, our set points for shutdown was correctly added to the system. What I do when I am in the field and I need to do the PID tuning is open a graph or a trend where I can see the variable, the set point, and the output value of my control valve, and I open another screen with the screen with the PID fields that I can change. So I do the change in the PID and I verify the trend to see what's happening. If you want to do the heuristic method to have preliminary values to add to your controller, no problem, but they probably will not be the last ones. And you don't need to worry too much about the final values that you have. What's important is not the values, is the stability of your process. Eventually, choose two different process engineers dealing with the same process at the same place will set different values for the PID, but both of them will get reasonable results. So more important that the values have the stability of your system. And remember that what is important is the stability of your process variable. And the valve, your control valve can open, can close, that is not an issue. Not necessarily you will have just one opening to have the stability of your system, because there are many influences in your system. Can be the environment, can be other process, pressure, temperature, if it's morning or if it's afternoon or night. All of these may impact the behavior of your control loop. So don't worry about that. The important thing is work with safe, use the trends, use the PID tuning, and do your best, because this is what we do as chemical process engineers working with plant design. And to finish this class, sometimes people asked me about books, and in this specific case I have two books to recommend. One of them is in Portuguese, so if you live in Brazil or if you talk Portuguese, I strongly recommend you to take a look. It is Controles Típicos de Equipamentos e Processos Industriais. It is very good book, because you have many kinds of controllers and the suggestions of the authors when you are dealing with compressor control of compressors, control of pumps, control of distillations, or controls of steam generator, and etc. So there is some basic information about the fundamentals, but it's not a book for calculations. It is to understand what's happening, and there are short calculations to define, for instance, the heuristics values based on the authors that I have mentioned to you in this live session. Another book, it is in English. You can find it in the Amazon. In both cases, I will let the link, affiliate link, available in the description of this video. I liked a lot this book, The Practical Process Control for Engineers and Technicians, because it is very concise, and although it talks about the calculations, the main purpose of the author is focus on the practical part, with many examples on how to do evaluations of the control loops, and we have also some theory about control and about instrumentation. So guys, this is it. I hope you like it, and I'll see you soon in the next video. Bye bye.